Bun găsit la emisiunea Știință și Cunoaștere! Ne aflăm la cel de-al treilea și ultimul episod al întâlnirii noastre cu cosmologia, un subiect abordat în premieră la Știință și Cunoaștere, deoarece este extrem de delicat, chiar dificil de explicat pe înțelesul tuturor. Dar acest neajuns a fost înlăturat de modalitatea atractivă, simbolică și simplificată prin care domnul profesor Max Tegmark a abordat-o într-o discuție maraton de aproape 3 ore, pe care am reușit să o înregistrăm în luna august. Știința a progresat atât de mult în ultimii 20 de ani încât pur și simplu nu am fi capabili să o înțelegem dacă, simultan cu aceasta, nu s-ar fi pus bazele filozofiei legate de rezultatele științei. Multă lume a auzit, de exemplu, despre teoria relativității restrânse. O formulă ușor de reținut și înțeles pe care oricine și-o amintește. Aceasta este E egal mc pătrat, care ne dă energia echivalentă ce se obține atunci când un obiect de masă m ar atinge viteza luminii. Teoria unificată a mecanicii cuantice este un manual de peste 1800 de pagini. Ea nu poate fi redusă și înțeleasă de către oricine. Și atunci a apărut o formă de filozofie care comentează rezultatele fizicii cuantice prin percepte și concepte filozofice, unul din ele fiind prezența observatorului. Dar vom reveni asupra acestor subiecte și cu alte ocazii, așa că până atunci vă invit să-l ascultați pe profesorul Max Tegmark vorbind despre universul matematic. Hello and welcome, dear Max Tegmark, for the third time in our program Science and Knowledge here on TVR Cluj.
Mulțumesc foarte mult, mă bucur.
Și eu de asemenea. And we are now going to continue our talks about the mathematical universe hypothesis, and this is what we would like to explore in this program. So first of all, let me ask you, why math?
As a scientist, if I look back at all of the science that we humans have ever done, I think there are two ideas which have turned out to be incredibly useful. One idea is that we should do experiments, measure things. And the other is that when we measure things, we should try to make mathematical models for our measurements. Now, why has that turned out to be so useful? It's been incredibly useful to the point that Galileo exclaimed famously that our universe is a book, written in the language of mathematics, and that was 400 years ago. Since then, we've had enormous further progress of mathematical descriptions of gravity, of light, of how atoms work, and how gravity works, Einstein's relativity, and so on and so forth, and to the point that actually in the 1960s, the physicist Eugene Wigner wrote a famous essay where he talked about what he called the unreasonable effectiveness of mathematics in the physical sciences, and asked why is this idea so powerful? Why is it so powerful to use mathematics to describe physics? And he felt that this is a question which really deserves an answer. Yet, so what is the answer? What I think the answer is, which is the key idea that my new book, Our Mathematical Universe, leads up to it, is that actually our universe seems so mathematical because it really is mathematical. And we'll talk more in great detail about what I mean by that. But if nature is at heart somehow completely mathematical, it's not so surprising that when we look more closely, we find these mathematical patterns.
So, at the very core of the tiniest things we explore in our world and in the universe is the mathematic, not the matter itself?
Yeah, so that's a very good question. We look around in the universe, where is all this math that people talk about? I don't see any big numbers written out there in the sky. And yet, when we look more closely, there are actually a lot of very mathematical things just built into nature. I should say that, first of all, what is mathematics? To some people, mathematics is just a form of torture invented by teachers to make us feel bad about ourselves in school, or maybe a bag of tricks for manipulating numbers. But what mathematicians have gradually broadened the idea of mathematics to also include shapes and patterns and many other things. And what Galileo was talking about when he said our universe is so mathematical was particularly shapes and patterns. If I throw something and I look at the shape in which it moves, this shape, which we call a parabola, has a very simple mathematical equation. If you call the distance in this direction x, you call this y, the mathematical equation is basically y equals x squared. It's a very simple equation. And similarly, if you look with a telescope out into the sky and look at what shapes are the planets going around the sun, what shapes are stars going around the black hole in the middle of our galaxy, these shapes are all the same shape. They're all called ellipses. An ellipse is basically a circle a little bit squished. So this is an ellipse if you look at my ring, from the side. So why are there all these shapes? We also have numbers, actual numbers built into nature. For example, if I ask how many pencils can I put that are all perpendicular to each other, the answer is 3, a number. We physicists have invented a name for this number. We call it the dimensionality of space. We say that space has 3 dimensions. But why is it 3, not 7 or 4? And when I weigh myself on a scale in the morning, I have a digital scale, so it also says a number. Maybe it says 87 kilograms. This number, you might think, is not really fundamental, because a kilogram, first of all, somebody else could weigh themselves and they would weigh something else. And the kilogram is something we invented, we humans. But if you take the weight of a proton and you divide by the weight of an electron, you get 1,836. And that number is really built into nature, because all protons weigh the same and all electrons weigh the same. And where do these numbers come from? We've discovered now, actually, that everything we've ever measured in physics we can calculate from just 32 numbers in principle, and then by doing certain calculations.
But let me also discuss this idea. We have, at least as I am guessing, or if I am correct, 3 levels of describing the universe. This is the matter level, which is very condensed, the energy level, which is less condensed but still measurable and visible, and the information level, which is maybe this is where everything is based on numbers and equations and the laws which make the energy level and the matter level in function. So the laws have had to be pre-existed before these 2 levels.
Yes, it does indeed seem as if these mathematical laws are in some sense more fundamental than the stuff that obeys the laws. And that is very much at the heart of what we'll be talking more about later in this program, that the very fabric of reality in some sense is mathematical. That's right.
So now I am guessing very approach, because I am not specialized in this field, but this is how I thought it would be possible to understand the mathematical universe, which is something, a level within the deepest, the smallest level possible that we had explored until present, based on what we know about energy and particles, and this is much profound level.
I feel it's very profound and very exciting. That's why I'm so interested in this, because I've always been very curious about the biggest questions and what is the true nature of reality. So the more profound and fundamental it is, the more interested I become.
Yes. have physicists discovered anything through mathematics? And can you give me some examples?
Yeah. So one of the most remarkable examples of the power of mathematics in nature is exactly what you mentioned here. When you can use mathematics alone just to discover something. Many things were discovered previously coincidentally. Somebody sailed to some place, discovered a new country, or somebody made an experiment and found a new effect. But if you ask about the planet Neptune, for example, or radio waves, or most recently the Higgs boson, all of those three things were actually discovered not with a telescope, not with a microscope, but with a pencil, doing mathematics. For Neptune, what happened was people had discovered the planet Uranus after the telescope was invented, and they looked very carefully at how Uranus was orbiting around the sun, and it seemed like it almost obeyed Newton's laws of gravity, but not quite. Uranus was moving a little bit funny. So independently in France and England, two different guys had this idea that maybe it's moving funny because there is a new planet we haven't seen. And then they used mathematics and calculated to see what properties such a planet would have to have. And one of them actually wrote a letter to an astronomer in Berlin and said, if on this day, at this particular time, you point your telescope to this particular place, you will there find a new planet. So this guy gets this, Gall was his name, this letter, and he probably thought, wow, this guy is cuckoo, this is ridiculous. But he was probably still pretty curious, so he took his telescope, he pointed it there, and boom, there is Neptune, a new planet, discovered ultimately with mathematics, with a pencil. And then history repeated itself many times. With radio waves, what happened was that James Clerk Maxwell had discovered these fantastic equations which described how electricity and magnetism work. And I mentioned in the last program that some of my students like to wear these equations on a t-shirt. So when he found these equations, he solved them. He realized that there was a new solution to his equations which corresponded to some kind of wave that could fly through vacuum, through empty space, very, very fast. And he calculated how fast it would go from his equations, and the answer he got was about 300,000 kilometers per second. And he thought, that sounds familiar, because that's how fast light travels.
Yes.
And he realized for the first time that light is actually also a kind of wave, an electromagnetic wave. And he realized that if light can travel through space, maybe we can also, with magnets and electricity, make our own waves, and that became called radio waves, and send them through empty space, and use that as a useful way of communicating with each other. This was all done with mathematics, just theory. Later on, scientists like Hertz actually built devices where they were able to actually show, wow, this works. And as a result, we now have our cell phones and the information society that we live in. And it was all predicted again with mathematics. And the most recent example that I want to give is the Higgs particle. Peter Higgs,
yes,
took all of the latest and greatest knowledge we had about particle physics and studied the equations and realized that for it to all really make sense, he needed to introduce some more stuff in one of the equations. And he predicted that if you built the biggest and most elaborate machine that humans have ever built, the Large Hadron Collider in Geneva, and if you collided particles together that are near the speed of light in a certain way, and you measured very carefully, you would there discover a new particle, the Higgs boson. As you know, the machine was built, and there it was. And it was predicted by mathematics.
So the Higgs boson is real after all?
Well, for many years, this was just a theory. But now, thanks to the fantastic work of physicists from around the world, including many Romanian physicists at the Large Hadron Collider at CERN, we found it. It's there. And this is another great triumph, I feel, for mathematics as a powerful tool for discovering things about our universe.
Yes, and but also there was an incident regarding that at a certain experiment, had been found some particle which could travel more than the speed of light. Can you tell me about?
Yeah, there were a lot of there were some particles which were discovered. They had made measurements, and it seemed like they made it a little bit faster than the speed of light, which would have violated the mathematical equations of Einstein's theory of relativity. And then eventually other people measured this more and more carefully, and it turned out the measurement was wrong. They had actually made a mistake. So the mathematics was correct, and the people were wrong.
So we are not yet above the speed of light.
No, and this is another example, again, of how powerful these mathematical equations are. It's truly really remarkable how well these equations and formulas have worked in describing our world.
In what sense do you believe the universe is mathematical?
Yeah, so that's a very deep question that you're asking now, because on one hand, yes, there are properties of the universe which correspond to numbers, but it seems like there are a lot of properties which are not mathematical. Like, I don't know, do you have a cat, for example?
No.
So if somebody, maybe one of the viewers has a cat and looks at this cat, and you ask, okay, what properties does this cat have? Maybe it's cute, has the property of being cute. Maybe it has the property of being fluffy. Maybe it's a little bit shy, a little bit mischievous. They don't feel like mathematical properties, right?
Yeah.
Yet we know that that cat is actually made of elementary particles, such as quarks and electrons. And what properties does an electron have? Well, it has the property -1, 1/2, 1, and so on. Now, we scientists have fancy names for these particles properties. We call them the electric charge, the spin, and the lepton number, but those are just words that we made up. The only properties that the electron actually has are numbers, mathematical properties. So the electron itself is a purely mathematical object in the sense that it actually has no properties at all beyond mathematical properties. You can't say that the electron itself is cute or fluffy or shy. It just has these properties like -1.
Well, these are concepts based on our emotional reactions to things.
Yeah, exactly. So we humans, when we see complicated things made of these particles, assign other properties to them too. But the basic building blocks of matter, all of the different kind of particles are purely mathematical in the sense that they have no properties at all except various numbers, mathematical properties. So you might ask, okay, maybe the stuff in space is mathematical, but surely not space itself. So what properties does space have? Well, we already talked about one such property, the property 3, right, the dimensionality. That's also mathematical. Mathematicians have also discovered other properties that space has, called curvature and topology, which are important in Einstein's theories.
Quantization of space.
When we add quantum mechanics too. But if we look at classical space, it has these other properties like curvature and topology. They are also, it turns out, purely mathematical properties. Here in the Cluj, in the math department at Babiš-Bolyai University, they study curvature and topology and dimensionality. So actually, space itself, as far as we know, is a purely mathematical structure in that it has no properties at all other than mathematical properties. So now, if space itself is mathematical and the stuff in space is mathematical, then it doesn't sound as crazy anymore, the idea that maybe everything is purely mathematical. And that's exactly the mathematical universe hypothesis that I talk about in this book, that we are simply part of this vast mathematical object, our universe. And the reason that we can approximately describe it by mathematics is because sometimes some complicated mathematics can be approximately described by some simpler mathematics. For example, if I have a sheet of paper which is approximately flat, you can write down some very complicated equation for this surface. You can approximately describe it as a flat piece of paper, which is simpler. And we humans discover these simpler approximations first, and gradually, as our physics research gets better, we discover more and more accurate approximations to the true mathematics. But the hope is that one day we can discover the actual correct mathematical equations which describe
But
our world.
how much of them are discoveries and how much of them are invented?
So this is a wonderful controversy, actually, not just among us physicists, but also among mathematicians. Is mathematics something which is discovered, or is it something which is invented? I believe that there is an external physical reality that's out there, independent of us. So even if I, Max Tegmark, didn't exist, there would still be a reality out there. And when I, as a scientist, study it, I believe I'm discovering what's out there. I'm not inventing it.
Yes.
But, you know, not everybody agrees. There are solipsists who believe that nobody except them exists. They're entitled to believe that. There are also much more serious physicists, like, for example, Niels Bohr, a founding father of quantum physics, who we discussed, who said things like, no reality without observation. So he would not necessarily accept this idea that the reality is independent. There is a reality independent of us. He felt that observation and us humans are, you know, very central. But I believe that we should be more humble and accept that there is that the Andromeda galaxy exists independently of us, and we discover these physical things. And what about mathematics? Well, it's very interesting. I have many friends who are mathematicians, and they usually also say that they discover things about mathematics. They don't invent them. For example, Plato was very interested in geometric shapes over 2,000 years ago, and discovered that there are exactly 5 kind of really regular three-dimensional shapes that are now called Platonic solids. The cube, which we all know, and then a tetrahedron, and then the octahedron, which is made of 8 triangles, an icosahedron with 20 triangles, and a dodecahedron. And those are the only 5 that you can ever make, which are completely irregular. And when he felt that he discovered the existence of the dodecahedron, he didn't feel that he invented it. He felt that it sort of was there, this mathematical structure, the idea of this perfect shape.
Maybe it's a combination between what we discover and it is valid and verifiable in all cases, and in sometimes we use equations, for example, adding and extracting the same number in order to create a better condition to solve the equation.
Yeah, that's a very nice example. So mathematicians, when they study different mathematical structures, they include not only shapes like the cube, but also things like numbers. The simplest kind of numbers are the ones we call integers, 0, 1, 2, 3, 4, and so on. And if you look at the numbers, I think almost no mathematicians would say that they invent the fact that 5 plus 2 equals 7. You can discover that it's 7 by making the calculation. And the universe, it feels like reality had no choice. You can't have mathematics where 5 plus 2 equals 8. It's inconsistent. And but what we can discover are useful tricks and methods for how to manipulate the numbers.
So they are invented.
Well, I'm trying to just give you a flavor of the range of opinions that people have. I mean, a lot of computer scientists would also say that then the algorithm, the method, we also discover. And it couldn't have been in the most, we learn in school a way of multiplying numbers, which is an algorithm, and there's an even more effective, faster one that computers use. And then there is one that you can prove that is the fastest, sort of, and the computer scientists would say that, again, these are also things we ultimately discover the methods. And if it's true that nature itself is a mathematical object, then this feeling that mathematicians have that they discover mathematics, and the feeling that we physicists have that we discover the Andromeda galaxy, we discover Neptune, are one and the same feeling of discovery. We learn more about what actually exists out there. And that's how I think it is. I firmly believe that we don't invent mathematics. we discover it. What we invent, it's very interesting that you asked this. What we do invent, though, are the names for the numbers. In the number 3, for example, in Romanian, we don't say 3, we say tre. In Swedish, we say tre. In German, we say drei. Those are inventions. Right?
Oh,
each culture invents its own name for the idea of 3, but it's still the same number, no matter what we call it. If you have a Spanish mathematician who says cinco más dos igual a siete, and an English mathematician who says 5 plus 2 equals 7, it's the same truth, because you can have a dictionary that says if you translate each of the words, the claim of one mathematician is the same as the other person's claim. Similarly, the way we write the numbers, we've invented. You know, in Western Europe, and in fact, all of Europe, we write the number 3 like this, and so on. But in India, they write the numbers differently.
The language in which we communicate the science. This has been invented.
This we invent. We invent the symbols, the words, the notation, but the basic structure is exactly the part which remains when you strip away all the baggage that we have invented.
Yes, but this is very useful because if we want to transmit knowledge, for example, someone is discovering something in Japan, and if he is using the common words which are translatable and understandable for all of us, then his knowledge can be shared to everyone.
That's right.
But
that's right.
If someone is discovering something which is very weird and is using too much symbolistic language and with no clarity of creating good explanation, then he would not be understood, but only by other people who share the same thinking method.
Exactly. So language is very useful, which is why we humans invent it. But we have to remember, nonetheless, that it was we who invented it. And this would become particularly urgent. Suppose in the future we were able to make contact with a civilization somewhere else in space. They won't share any of our language. Then we have to work very hard to establish some form of communication. And when you explain to a computer how to calculate something, again, you have to get rid of all the human words because the computer doesn't understand Romanian, and only look at the abstract mathematical structure, which is what's left when you take away the language. And this is also very important in physics because we have if you take the basic equations of mathematics that describe our world, like we talked about in the last 2 programs, and you solve them, you find, oh, there is a solution to these equations that corresponds to a bunch of quarks and electrons that form a very stable object here. And then you find that there are many of these in different places in space. Then it becomes very convenient to invent a name for this object. So we call it atom. And then you work some more on the equations, and you find that sometimes you get 10 to the power 57 atoms that clump together in a big ball in space that shines off energy. And then we realize, oh, when we solve the equations, you have many of these. Then it becomes convenient again to invent a word for that. We call it a star. So it's very good that we invent these words, but it is still we humans who invent the words. If you were, in principle, a very, very talented mathematician could, by just studying the equations, figure out that there are stars and all the properties of our world without using our language. And in this sense, it's actually possible to describe things purely mathematical.
Yes. However, our world keeps changing, but mathematical structures don't. So how can they be the same?
Now that's a very important and subtle question. For example, the abstract cube is just this object which always has 6 faces, always has had 6 faces, always will. There's nothing that changes about the cube. Whereas our world, things are happening. How can those two be the same? Well, Einstein taught us a very interesting lesson about this. Einstein said that there are 2 different equivalent ways of looking at our physical reality. We can either think of reality as being this 3-dimensional place where stuff happens over time. where there's change. Or we can think of reality as being a four-dimensional place, where time is just the fourth dimension and nothing ever happens. And he called this way of thinking about it space-time. So if we think of our life as a movie, then space-time is the entire DVD. And there are different ways you can think about the DVD. You can play it, and then you think of things as happening, but you can also just look at the DVD itself. It's a static, unchanging object. And encoded in this DVD is a grand drama with people, with things beginning and people falling in love and problems and so on, and then ending. But the DVD itself is not changing. So this is Einstein's way of thinking about the physical world as this four-dimensional reality that contains the full story. And it is that Einstein four-dimensional reality which is a mathematical object.
Is the theory of quantization of space and time more still valid or not? Is time and space have really the smallest quantum time ever possible to exist, and also the smallest length the universe is capable of, or they are invented too?
So you just asked the most embarrassing questions facing physics today, which is it's very important that we put on the table, because the truth is we have these two very successful theories in physics. We have Einstein's theory of general relativity, which describes all the big things in our universe, and gravity, and it works very, very well. And then we have this other theory of quantum mechanics, which we talked about in the last program when we talked about the level 3 multiverse, which describes small things and atoms and how computers and cell phones and other technology works. Also very successful. But these two theories don't really like each other. And we have still to this day failed to find a mathematical set of equations which combines the two of them to everybody's satisfaction. And this is if you can figure out how to do that, I can guarantee you will get a free trip to visit my hometown of Stockholm and collect your Nobel Prize in physics. Because it's the most embarrassing, outstanding problem for theoretical physics. What I think we can also say, though, is that there are many different approaches that try to unify quantum physics with gravity. We don't know yet which one of them is right, if any. But all of the different candidate theories that are competing are all completely mathematical again. So there is really no indication that the conclusions we were drawing about things being mathematical will change. String theory, for example, the most popular attempt, is an extremely mathematical theory. It's so mathematical, in fact, that Ed Witten, one of the most famous string theory pioneers, got the Fields Medal, which is like the Nobel Prize, not in physics, but in mathematics. So it seems like whatever the true theory turns out to be, it's very likely it's purely mathematical.
It will also have some philosophical consequences. If, for example, the time and space would be quantized, then that means they would have just like an oscillating signal, rectangular signal. This is 1, and the other semi-period is 0 or non-existent. So if time is quantized, then it had to be a series of 0 and 1, 0, 1, 0, 1, which means at 1, when it is 1, a Planck time, all the universe is here with everything as we see. On the next Planck time, the universe is gone, and this is nothing.
Well, you're asking exactly the kind of questions now, like where you need a unified theory of quantum mechanics and gravity to give an answer. What happens when you look at things that are so small that you need quantum mechanics, but also so heavy that you need gravity? And we can't answer them because we don't have that theory yet. I think what's safe to say, though, is that, the sort of space that we have now and the time that we think intuitively we understand is probably only an approximation to something deeper.
Yes.
Just like we talked about how an approximately flat surface can be approximated by being perfectly flat. That's simpler math. The true nature of space and time is probably different, but approximately like this. Even the air in the room that lets you hear me now because of the sound waves feels like it's very continuous in a smooth medium, right? And we can write down equations for how the waves move, which make the assumption that you can divide space into infinitely many little pieces. We know that's wrong because we know that actually the air is made of atoms. There's only a finite number of atoms. And the only reason that the air feels smooth, I blow like this, is because there's so many atoms. The atoms are so close together and so small that it averages out to something very, very smooth. And in the same way, it's quite possible that the space between us also is made of some fundamental building block that's not smooth and continuous, and that it's only because
Fundamental geometrical building blocks.
Yes, exactly. Yes. There might very well be some fundamental geometric building blocks, maybe of some quantum nature. The physicist John Wheeler, for example, speculated that maybe if you look at space, if you could zoom down and stretch things out so that everything gets 10 times bigger, and then you do that 34 times in a row, you would see what he called quantum foam, that space becomes really fuzzy. And we have good reason to think it doesn't even make sense to talk about any distances that are smaller than 10 to the power minus 34 meters, because our whole idea of space probably breaks down. But nonetheless, these questions which string theory and other approaches are trying to tackle all have in common the idea that it's all mathematical. It's different mathematics then, maybe with different geometric concepts that are the building blocks. But it's still mathematical at heart. And this is, again, this basic idea and talking about how it seems like like the basic fabric of reality is mathematical.
Please tell us more about your book.
Sure, yeah. So as you can probably tell, I'm very excited about these ideas, and I have been very excited about them for a good part of my life. And I wanted to share some of this excitement with a broader audience in a way that's easy for any intelligent and interested person to understand, even if they haven't spent any time at all studying physics in school. So this book is both my attempt to explain some of these exciting ideas and also a bit of my personal journey. I divided it into several different parts. So the first part of the book talks about all the great discoveries we've had in cosmology, our first program, basically, and how we've learned more and more about how big our universe is and parallel universes and such. The second part of the book talks about instead the question, what is everything made of? When you look to smaller and smaller scales, quantum mechanics and all these fascinating things we talked about in the last program, and the level 3 parallel universes. And then in the third part of the book, I talk about what we've discussed here today, how it's so mathematical and what that means, and how that even gives evidence of a still bigger level 4 multiverse. And I should also say the subtitle of this book, which is available now on Amazon for pre-order, and anyone who's interested in talking with me about the book also is very welcome to visit my Facebook page. You can ask questions and I'll be delighted to answer. It's Our Mathematical Universe, My Quest for the Ultimate Nature of Reality. So this book, even though it's mainly not about me, but about our universe, it's sort of through my eyes. I talk a lot here about my own experiences and adventures and misadventures, the disappointments when things have gone wrong in our work, and the excitement that I've had the good fortune to be part of. And I hope also that the person who reads this book will come away with more of an appreciation for how exciting our universe is and how fun it is to be part of this detective story to try to figure out more about how our reality works. So another interesting implication, if this is true, that our universe really is completely mathematical, then you can make an argument, which I make in the book, that the level 4 multiverse that we talked about last time actually exists, so that our reality is even bigger. Even if string theory turns out to be wrong here in our universe, there is another universe where string theory is correct. So it, in a way, gives us the grandest possible reality. And I think that if it turns out that I'm wrong, that means that our universe, that our quest for knowledge and understanding will eventually hit a roadblock beyond which we can't proceed, because things are not mathematical anymore, and we humans, no matter how hard we try, just can't understand and predict things. But if it turns out that I'm right, then I think that's very exciting, because then there is no roadblock. And we can continue our quest to understand our reality better and better, and we're only limited by our own imagination.
So there is no such things like the end of science, which a writer predicted in his book, The End of Science. You know, I don't recall his name.
Well, if I'm right, then there will not be an end of science, because we hit that roadblock where things are no longer mathematical. The only thing, there might be an end of our imagination and creativity, but I think that's always been the challenge for artists and poets also, to become more creative and imaginative. And that's what I very much hope for, that we will have this, that it will be up to us if we have enough imagination to continue figuring things out.
Also, and I don't know how much time we have, there is an interesting theory which I found about, promoted by Michael Talbot, the holographic universe. Is the universe really holographic?
We don't know. The holographic principle is an idea which is a key part of one of the approaches to quantum gravity and unifying gravitation and quantum mechanics. We don't know yet whether it's ultimately going to be correct or not. I think it's very important in a situation like this, where we don't know what the right answer is, that we pursue all different ideas that are out there. And because if everybody is just doing the same thing, we're much less likely to have one of us actually find the truth. So even if it turns out to not be correct, we should definitely study it.
How this information can help us get a better life for ourselves.
Sure.
In order to, for example, to apply some philosophical concepts, philosophical theories in our life. For example, if quantum mechanics said, if you are observing a certain very intimate phenomenon, then that phenomenon is changing. If you observe a particle, the particle is behaving like a wave. If you are observing a wave, the wave is behaving like a particle. And for example, some biologists said that if you are doing this kind of observation, of a conscious observation through your body, you can change your physiological parameters of the body, just to observe them. And you can observe, you can change them. So they want to apply what they call the quantum biology, but it is not quantic. It's not just taking the philosophical concept and to apply in a real phenomenon, to do real changing.
So that's one out of many examples we can give of how using mathematical equations to understand our reality better, we can develop powerful new technologies. And I think to bring this back to home and ask, what does this mean for us humans on this planet and for us personally? It's very important to maybe look at all of these three programs and discussions we've had and say, what have we sort of learned? And this gives a different perspective. For me as a cosmologist, my perspective is that there's this small little ball in space, our Earth. There's 7 billion of us living on there. And in this vast universe, we've learned that life is very rare, and we're very fortunate to be on such a habitable, life-friendly planet. And we've also learned that we have these fantastic technologies that can do wonderful things for us, and technologies which can destroy us. So I feel that as a species, life has reached the fork in the road where we have to really make a choice. Either we will take the paths of death and destruction, and because for the first time in the the history of our universe, there's a species that actually has the technology to destroy itself. Or we can get our act together and build something truly remarkable and wonderful together. And maybe in the future, in the distant future, life can spread from our planet out into our universe. Maybe one day our entire universe can come alive. And I think, as we talked about in the first program, we are not at all insignificant, because we might be the only planet in our universe which has this technology. And we are also not insignificant, even though our lives are short. You know, if we eat our vitamins and exercise, maybe we can live for 100 years, but that our universe is 14 billion years. It might feel short, but this period right now in our lifetime might be when the big fork in the road happens, when we have to decide whether we can get more organized as a species and focus on what's really important, or whether we self-destruct. So I think, again, for the viewers out here, especially children and teenagers who are thinking about what to do with their careers, you should feel very empowered and realize that what you do here on this planet in your lifetime, what you choose to study, how you choose to change society, can change not just the course of life in Cluj or in Transylvania, or on Earth, but for our entire observable universe. It's amazing. And so I think the more we appreciate this perspective, I think the better our chances that the future of our universe will be a worthy one.
Well, I thank you so much for this meeting and have such a nice talks in these 3 programs. And I hope that we can meet at least once per year, every year. Are you going to visit Romania next year, in 2014?
Mi place foarte mult Transylvania, and I, of course, love my family here in Cluj, so I think it's safe to say that I will be back many, many times, and it's been a real pleasure. Mulțumesc foarte mult!
Mulțumesc și eu, și mi-a plăcut să avem această conversație și aș vrea să o continuăm atunci anul viitor cu ocazia unei noi întâlniri.
Foarte bine!
A 3-a parte a discuțiilor a fost mai scurtă, cu 9 minute, așa că am profitat de promisiunea profesorului de la Facultatea de Chimie, Adrian Pătruț, de a reîncepe să participe la Știință și Cunoaștere și l-am invitat să ne spună câteva concluzii legate de cele 3 părți ale interviului cu profesorul Max Tegmark, cosmolog de talie internațională la Institutul de Tehnologie din Massachusetts, Statele Unite. Adrian, mă bucur că ne întâlnim din nou la Știință și Cunoaștere. Tu ai o viziune largă asupra științelor și ai participat la emisiuni foarte diversificate ca domenii și ne bucurăm să te avem din nou alături.
Pentru mine emisiunea aceasta cu Max Tegmark a fost o surpriză foarte plăcută, fiindcă, dacă îți amintești, de multe ori ți-am spus că este necesar să facem emisiuni despre cosmologie, care sunt complicate. Ai găsit un om de primă mărime, un om de primă mărime pe plan mondial, care ți-a dat niște interviuri, le putem comenta, ne putem adresa publicului larg, putem face un dialog și este un mare succes. Mai înseamnă că este încă o temă importantă pe care trebuie să o dezbatem și să o găsim, problema aceasta a evoluției omului, care este astăzi în dezbateri foarte interesante, sunt noi descoperiri și care merită să fie studiate, sunt punctele tare ale cercetării științifice. Tegmark a avut un articol de referință în 2004, în februarie, în Scientific American, în care a descris cele 4 tipuri de lumi paralele, unele care sunt foarte asemănătoare cu ale noastre, altele mai puțin asemănătoare, în care putem avea un alter ego, în unele dintre ele, în altele nu. Aceste lumi nu prea pot comunica între ele, sunt situații speciale aici. Aici este problema de a crede sau de a nu crede. Este foarte greu de adus dovezi în favoarea lor. Există anumite elemente pentru care anumiți psihologi preferă astăzi, anumiți fizicieni preferă astăzi, în loc cu interpretarea Copenhaga clasice a mecanicii cuantice, acea interpretare a universurilor multiple, a lui Evans și Everett, care este interesantă și care spune, de exemplu, că eu, dacă vin, de exemplu, la studio pentru un interviu, atunci eu pot să vin cu grosier cu autobuzul 30, pot să vin cu taxi sau cu autobuzul 28 și lumea se scindează în 3 și eu apar în 3 lumi diferite și evoluez diferit în fiecare dintre ele în funcție de opțiunea mea și la fiecare acțiune pe care o am eu și fiecare alt om și fiecare altă ființă și până la particule microfizice, universul se scindează în atâtea universuri câte probabilități există. Toate acestea evoluează independent și paralel. Deci sunt universuri în care noi nu existăm, altele în care am existat, dar avem un destin diferit, în care ne-am născut în alt moment, în care unele am murit deja, în altele ne vom naște, în unele suntem probabil preoți, în altele suntem oameni de știință, etc., etc. Deci este o teorie foarte interesantă, foarte greu de demonstrat, dar care, datorită unor observații cosmologice de astăzi, referitoare la galaxii îndepărtate, la cuasari și la roiuri de galaxii mai ales, sunt preferate de către unii cosmologi față de teoria clasică, cea de la Copenhagen, care spune că se alege o singură probabilitate, pisica Schrödinger și așa mai departe, colapsul vectorial al funcției de undă și că tot timpul se face o selecție și că noi avem, ca și observatori conștienți, posibilitatea de a influența tot timpul realitatea fizică. Deci nu suntem observatori doar, ci suntem și participanți în această lume. Și că universul este chemat la manifestare și se alege opțiune care este oferită tocmai de mintea noastră, care face această selecție în momentul observației. Deci actul ăsta este esențial. În teoriile celelalte, în teoriile universului multiple, practic tot timpul are loc. Universul se divide în N universuri în funcție de probabilități existente și nu mai există această acțiune directă a observatorului în momentul observației.
Și cu ce viteză se divide el, dacă se divide? Se divide
la fiecare eveniment cuantic, acum am avut
fiecare secundă, microsecundă.
Am avut o observație aici, un caz macrofizic, dar practic aceasta se petrece la nivel microfizic. De câte ori particulă microfizică se spune că este emisă și poate trece prin 3 fante, universul se scindează în 3. Într-unul trece prin fanta A, în altul prin fanta B, în altul prin fanta C. Da? Și aceasta se întâmplă de N ori în fiecare fracțiune de secundă. A existat astăzi peste 10 la 80 de universuri paralele care evolua independent. Și fiecare o istorie proprie, ele nu pot comunica între ele, deocamdată credem, și o poveste fascinantă, de așa un fel de multivers și deodată lumea este mult mai bogată decât credem noi și toate visele sunt posibile, unde toate iluziile sunt reale, nu? Deci istorii sunt complet diferite.
Da, da. Aici mai este un element. În momentul în care ezoteriștii au auzit teoria asta în care totul devine posibil, au luat și au implementat-o în modul în care totul devine posibil, dar aici în lumea noastră.
Bine, acum...
Deci,
acum povestea...
Și încep să creadă din nou în acele lucruri care n-au nicio legătură cu lumea noastră.
Da, acum întotdeauna curentele ezoterice, aceia care vin de la Blavatsky încoace, trecând prin mișcarea teozofică, prin Alice Bailey și așa mai departe, prin toate poveștile acestea interesante, prin Charles Leadbeater, prin Annie Besant, au încercat să găsească descoperiri științifice care să justifice teoriile lor. De exemplu, atunci când a apărut radioactivitatea, s-a spus că radioactivitatea aceasta, descoperită de Becquerel și confirmată pe urmă de către Irena Skłodowska, ulterior Madame Curie, practic eu am spus că radioactivitatea aceasta este domeniul eteric și poate astral și cum emite atom astral soarele și ce frecvență au ei și a spus că în sfârșit au descoperit numai această ezoterică ascunsă oamenii de știință. Până au văzut că nu este, am tot felul de descoperiri științifice care au încercat să fie exploatate de către toți cei care susțin doctrine mai puțin ortodoxe în punct de vedere științific în favoarea lor. Deci întotdeauna când va fi o descoperire științifică, se va spune că aceasta confirmă teoria noastră, până când se va vedea că o infirmă și va fi o altă descoperire științifică și mai departe. Deci întotdeauna spuneam cândva că cele mai bune profeții sunt cele care se fac după ce evenimentul s-a împlinit. Da? Cum este cu sfârșitul lumii, că n-a fost în 2012, că va fi în 2022 sau în 2013 sau ceva, întotdeauna a trecut momentul și spune nu, că s-a greșit, va fi peste 10 ani. Și tot așteptarea aceasta trebuie să fie menținută. Pentru că trebuie să ai un număr...
Există o nouă dată a sfârșitului lumii?
Evident.
Care?
S-a spus cu 2022-2023. Deci totdeauna există noi date pentru că există o masă de credincioși acolo care te susțin, ai un cerc de adoratori undeva care susțin aceste mișcări ezoterice și care trebuie să nu fie dezamăgiți niciodată. Păi domnule, da, s-a greșit acolo o interpretare greșită, cu tare, dar o așteptăm din nou și va veni. Deci nu trebuie să omori speranța.
O lovitură mare acum cu 2012.
O lovitură mare a fost faptul că media și foarte multe instituții care trebuie să fie bine informate au crezut în așa ceva. Inclusiv oamenii de știință care au făcut niște profeții înspăimântătoare, care nu știu ce s-a întâmplat cu ei și în România și în alte țări. Deci au mușcat aici, să spunem, la această nadă care este cu mileniarismul, cu sfârșitul lumii, care de nu știu când povestea aceasta. Nu are o tradiție de peste 1000 de ani. Deci, totuși, undeva și noi făceam emisiuni și undeva ascultătorii erau dezamăgiți când spuneam că nu va fi. Deci chiar dacă oamenii doresc să trăiască clipe dramatice, au nevoie de adrenalină, care le creează senzații deosebite și așa mai departe și se gândesc cu oroare, dar și cu un oarecare orgasm, între ghilimele, spun, cel puțin intelectual, dacă nu fizic, la anumite evenimente dramatice care ar putea aștepta și cu care ar putea fi contemporani, chiar dacă acestea i-ar afecta. Și mulți au fost dezamăgiți că nu s-a întâmplat nimic îngrozitor care să strice acest echilibru.
Păi nu dar nici măcar o calamitate naturală n-a venit în 2012, cum a fost în 2004, și care anul 2004 nu era nicăieri pe nicio listă profetică că ar urma să se întâmple ceva. Și deci 2012 a fost chiar un an liniștit, fără războaie, fără nicio bombă atomică, fără furtuni deosebite, uraganul Katrina și altele.
Da, sigur. Deci... Dar vezi că lumea a devenit în esență tot mai puțin culturală, mai puțin științifică în ultimii ani, pentru că oamenii sunt interesați nu de aflarea adevărului, ci de căutarea profitului. Foarte mulți, inclusiv în România, unde, de exemplu, nivelul învățământului a scăzut dramatic față de acum 20 de ani și a cunoașterii la nivel de masă. Și atunci oamenii sunt tentați să aibă astfel de... să creadă în lucruri foarte simple și foarte naive de multe ori. Deci acest adevăr științific este foarte complicat ca să fie înțeles de către omul obișnuit care nu are o pregătire suficientă în fizică, nici în alte, în cosmologie, să explici lui de ce este necesară evoluția umană, pentru că practic, sau evoluția biologică, fiindcă aceasta este doar o etapă în evoluția întregul univers ca și ansamblu, de la Big Bang încoace, că tot universul practic se află într-o evoluție, nu? Că este o problemă foarte mare aici și de ce este necesară evoluția? Fiindcă practic universul are anumită energie inițială, mă rog, foarte mare și această densitate de energie scade în timp prin expansiune și atunci trebuie undeva să fie compensată. Deci ca universul să poată evolua, atunci se creează ansamble din ce în ce mai mari, care sunt tot mai sărace în energie și ele pun în libertate energie și universul poate evolua în continuare, nu? Se obțin din particule simple, particule compozite, se obțin nuclee, se obțin atomi, se obțin molecule, se obțin mai complexe și se tot pune, se eliberează energie care permite universul să evolueze în continuare. Deci evoluția este un factor necesar și obligatoriu în universul ca el să existe.
Mulțumesc foarte mult, Adrian, și atunci te așteptăm cât de curând.
Și eu mulțumesc.
Aici s-a încheiat și ultima parte a seriei dedicată cosmologiei, singura știință care îndrăznește să caute răspunsurile la marile întrebări existențiale și la neliniștile noastre metafizice. Și religia încearcă să facă aceasta. Nu e nicio concurență între cele două, ci probabil că e o completare, însă de pe poziții foarte diferite. Înainte de a încheia, doresc să vă reamintesc din nou faptul că domnul profesor Max Tegmark vă stă la dispoziție pe pagina sa de Facebook cu orice întrebări legate de cosmologie și chestiuni discutate în cadrul emisiunii. Fiți alături de noi data viitoare la o nouă întâlnire cu știință și cunoaștere.